Okay, so let me talk about the GPC mechanism. I kind of briefly mentioned to you about why the higher molecular weight is coming out first, and this kind of picture is discussed in many places, and I want to discuss it one more time. This is a picture from the waters.com. Let's think about this is a big polymer chain, and this is smaller polymer chain. Big polymer chain trying to get it into the pores, but well, no, I can't. So they're just coming out like this. Whereas the smaller polymers, like they because they are small enough, they can kind of the way that has a more ways to explore the spaces. So for a given time, their effective path lengths, due to the gain in the entropy, in translation entropy, they span the column longer. So therefore, larger one comes out first. So let me use the smaller chain. So here, this is a blue one, and then the blue chain is fall behind because they go in and out through this. So you see this highlight. So I want to highlight here, right? So if you're looking at this picture, the authors are trying to show it to you that, okay, so if you have a smaller chain, they have a chance to go in and out, right? So it's more like a explore the inside of out, whereas the larger polymers do not have a chance. So they kind of stay in the outside. And that's why this picture is about. So you do not have a chance to go inside. You just kind of go in and out. So you are not really effectively having a longer path. Whereas, as you can see here, the blue chains has a more times to go in and out. So they are the one who falls behind. Okay, so this is make the effective lengths to come out. So then therefore this is a smaller molecular weight, smaller chain. And then this is the larger chain, which is a molecular weight is high. So as you can see that what's coming out first is this is a retention time. We also call it as a elution time. So retention time, elution time, which is the same as can be converted into the retention volume or elution volume. Just a different community use the same thing because at a fixed flow rate, volumetric flow rate, okay? Volumetric flow rate, which is typically fixed at, for example, 1 milliliter per minute. Or common one is 0.5 milliliter per minute. So that's the time that they fix it up. So we can just use this one vice versa. So therefore, if you look at that, the larger polymers will come out first. So this is the larger polymers that come out as a band first, and the smaller polymers fall behind here, right? So eventually, the smaller polymer, as time goes on, will come out as a coming after the peak. So therefore, this is a high molecular weight, and the one behind is low molecular weight. Okay, so and then they look at the peak molecular weight and making a GPC calibration curve if it is for the calibration process and so on. Okay, and I kind of briefly mentioned about the detector. And the detector is what is called the DNDC detector, or the refractive index detector. So what do they see is based on you remember the DNDC that I talked about, light scattering? So the refractive index difference between the N polymer minus N solvents. Okay, so that's what I'm going to have I think I'm going to make a separate short section on the detectors. I'm going to talk about it, but let me just continue to talk about this idea. So idea about the GPC mechanism is size exclusion. Okay? The size exclusion idea is shown up here, and then there is a little simple math that I can introduce to you guys. So I will just give you an idea. This is actually some of the SEM pictures of the polymer bead that is using to generate some effective pore. And this one is actually made by styrene monomers with the divinyl benzene. Okay, those are the main components they are using for making this porous material, porous cross-linked polymer bead. It's called a polymer bead. The reason say they're polymer bead is this is really big, and this is actually made by suspension polymerization. If you haven't heard of suspension polymerization, let me know. I can answer that in the Google Doc documents for the follow-up. But anyway, this one is essentially once again, though, you can think about polymer. This bead has a lot of pores, and I'm just giving you the idea about. Okay, it do not have a uniform pores. It just has these pores, and when you have a polymers big, right? Think about this. This is a big polymers, and they're kind of like this, right? But when you have a small size pore, they have a ways to go in and out, because it has a gain in the translation entropy. And if you think about the path that blue passes versus the red, the blue takes a longer. So that's why these things are coming, fall behind in the retention time or elution time. And this is essentially crossing polymer bead, right? So this is a polystyrene with a cross-linked, which is it's like a white large powders, and then this. So these pictures can be shown in here. So I'm going to show as a pore with some defined. So this is a more cylindrical pores, and then whose pore diameter is, let's say, is an A. And then we are going to consider polymer chain like this, and whose size is something like on R. Okay, it is not radius gyration, but it is related to some sizes, and that's related to the radius gyration. It's not exactly radius gyration, but we can think that this is a similar comparable size that is closer to the radius gyration. So you can relate that. Anyway, when this one comes in, and this is a center of mass of this polymers simplify into a bead, really the closest that can go inside is about here. Right? So that is that's sort of how the effective. This is the volume that this polymer chain go in and out, right? And then the other spaces that I highlighted, I can highlight it here as a yellow, right? These spaces. This spaces is not accessible for this polymer chain, because you have to really squeeze your polymer chain down to it, right? So this is a model for what is called a cylindrical pore. And then we can essentially define something called K. K is accessible volume fraction, and then the K is now what is a total volume, which is a pi a square. That's the area of this cylindrical pore, and that times L. And then what's the area that is accessible volume? That's A minus R. If you're looking at those, that's R. So therefore, this is an A minus R. That's accessible volume. So that's a square times L. Okay, and they cancel out, and this one, K accessible volume factor, becomes now 1 minus R over A to the square. Okay, and so now R, it should be smaller, at least the same as 1, and that can be, I guess the smallest one is a 0, and that's the ranges that where the chain can, and this scenario can be taken into account. So what that means is if your molecular weight goes up, your size goes up, and therefore your K value will come down, right? Remember, the K value is always smaller than 1, so what that means is polymer elute before the elution of solvent. Okay, and then this is the same argument. When the molecular weight comes down, R becomes smaller, your K value goes up, and to the maximum pore spaces they can allow to do. So this one essentially showing to the correlation between molecular weight and essentially the retention time, retention volume, in a way that what are the accessible volume fractions. So this is a K is related to the volume fraction, that is related to certainly the elution volume, retention volume. So this inverse relationship can be understood in terms of this relationship.